So, today we're going to talk about a mathematical idea. But trust me, this isn't some dry, abstract thing. This is an idea so powerful it completely changed science, it helped kickstart the Industrial Revolution, and yeah, it even helped put us on the moon. It's an idea that basically turned the headache of arithmetic into the engine of the modern world.
And get this, the main tool that the engineers on the Apollo missions used, the thing that did all the heavy lifting when they were designing those massive Saturn V rockets, it wasn't a digital computer. Nope, it was something way older and honestly, way more clever.
To figure that out, we actually have to jump in a time machine and go back more than 400 years, to a point where science was hitting a massive wall, a crisis of calculation. Right. So our story kicks off in the late 16th century. It's this amazing time of discovery, but also a time of just incredible frustration. Astronomers had this brand new way of looking at the universe, but they were literally drowning in numbers.
You see, the whole shift to a sun-centered solar system, what a brilliant leap forward. But in practice, it was a total nightmare. If you wanted to prove it or predict where the planets would be, you had to do endless, unbelievably complex calculations, multiplying and dividing these enormous numbers, all by hand with a quill pen.
And this whole problem really came to a head with two guys who changed astronomy forever. First, you've got Tycho Brahe. He was this genius at observation who created a flood of the most precise data anyone had ever seen. And all that data got dumped on his assistant, Johannes Kepler. Poor Kepler then had to spend years, literally years of his life, doing mind-dumbing arithmetic just to figure out the orbit of Mars. And here's the key takeaway. Science was completely stuck. The bottleneck wasn't a lack of ideas, it was arithmetic.
The solution that finally broke this deadlock was just an idea of pure genius. It was a new kind of math that, to the people at the time, must have seemed like some kind of strange magic.
So what exactly is a logarithm? Well, put simply, it just flips the whole idea of exponents on its head. So instead of asking, hey, what's 10 to the power of 3, a logarithm asks, what power do I need to raise 10 to in order to get 1,000? And the answer, the logarithm, is 3.
And when you see them side by side like this, it just clicks, you know? They're really just two sides of the very same coin. The exponential form gives you the end result, while the logarithmic form tells you the power you needed to get there in the first place.
Okay, this is where the real magic happens. These three properties are the entire reason logarithms are so amazing. By turning your numbers into their logs, you could swap these horrible, difficult multiplication problems for just simple addition. Division, that just becomes subtraction. This was the game changer, the breakthrough that would save Kepler and generations of scientists after him.
Now, an idea this powerful couldn't just stay on paper. No way. It had to become a tool. And the story of how it actually got into people's hands is this fantastic tale of invention and teamwork.
So you have these two guys, John Napier over in Scotland and Joost Bürgi in Switzerland, who both, totally independently, came up with the core idea. But it was an English professor, Henry Briggs, who made it truly useful for everybody. He actually worked with Napier to create the base 10 system that we still use today, a system that fits perfectly with our numbers, and then he spent years calculating the log tables that would power science for centuries.
Now, the tables were great, but the real revolution was turning that abstract idea into a physical object. And this is the tool that sent us to the moon, the slide rule. It was the world's very first analog computer, and it completely took over the worlds of science and engineering.
So how in the world does this thing work? It's so simple, it's genius. See, the numbers on the scales, they aren't spaced out evenly. They're spaced logarithmically. So when you slide the little 1 over to line up with the 2, you're physically setting a length that's equal to the log of 2. Then, when you move your cursor to the 3 on that same sliding scale, you are physically adding the length for the log of 3. Your total length is log of 2 plus log of 3, which the rule shows you is right at the log of 6. You're literally doing addition with your hands to perform multiplication. How cool is that?
And for 3.5 centuries, think about that. This simple device was absolutely everywhere. It built bridges, it designed airplanes, and yet it calculated the trajectories for the Apollo missions. It was the pocket-sized supercomputer of its day. And then it just disappeared. The moment the first affordable scientific pocket calculator came out in 1972, the slide rule became obsolete. Instantly, the entire analog era of computation was just over. But the story of the logarithm? Oh, that was far from finished.
So when the logarithm lost its job as a calculation tool, its second life began, and you could argue this one is even more profound. It stopped being a way to calculate, and it became a way to think and to measure our world.
What does this number mean? 32 times? Well, it's the difference between a major disaster and a truly world-altering catastrophe.
We've all heard about the magnitude scale for earthquakes, right? But what most of us don't really think about is that it's a logarithmic scale. That's so important. A step up from a 6.0 to a 7.0 isn't just 1 unit more powerful. It's a staggering 32 times more energetic. The logarithm here is what lets us even get our heads around this huge range of power.
And this chart just makes it so obvious, doesn't it? The jump from a 6.0 to an 8.0 isn't twice as bad, it's almost 1,000 times more powerful. A normal linear scale just couldn't show you that reality in any useful way.
And we use this same way of thinking everywhere. You know, for sound, a 10 decibel increase isn't just a little louder, it's 10 times more intense. In chemistry, a 1-point drop in pH means something is 10 times more acidic. Logarithms are the language we invented to make sense of the universe's most extreme scales.
So let's just take a second and trace this incredible journey. The logarithm didn't just solve one problem and then disappear. It evolved with us, changing its job as our own needs changed over time.
It's really like a 4-act play for a mathematical idea. It was born out of this desperate need. It was forged by these brilliant inventors. It was embodied in this iconic tool for centuries. And finally, it was reborn as a fundamental way we actually conceive of reality itself. It went from a tool for doing to a tool for thinking.
And that kind of leaves us with one last thought. We face our own computational crises today, right? We're trying to manage these huge data sets, model incredibly complex systems like the climate or AI. So the real question is, what brilliant, simple idea, what new logarithm is just waiting out there to be discovered? An idea that'll change not just how we calculate, but ultimately how we see the entire world.